Hello everyone, Ray Gallucci again. I'm going to talk on tidal asymmetry. And for those of you who were at last year's conference, one of the last papers that came up was by Scott Hall, who isn't here today, and he talked about making waves. And as part of his discussion on waves, he got into a little bit as to what really causes the tides. Everybody, oh, it's the moon, it's the gravity of the moon. Well, really, is it that? And I'm just going to read a little excerpt. If you pick up last year's book, I think it's the last paper because they're alphabetical. And I'll just read a little excerpt from what he said, and I'm going to blame everything that I say today on him.
Here. I agree.
I like Scott. I wish he was here. Everyone has heard that tides are caused by the gravitational attraction of the sun and moon. I've never heard anyone comment on the absurdity of this statement. How on earth can the gravity of the minuscule moon outmuscle the gravity of the earth and substantially lift huge quantities of water from the oceans? Similarly, why would the distant sun have any gravitational effect on the oceans? To illustrate my point, then he does some calculations, and he says, calculating the ratios yields the following. The attraction of the Earth is 290,000 times greater than that of the moon, and 1,600 times greater than that from the sun. At the ocean's surface, the gravitational effect from both of these bodies should be negligible. However, and he was advocating an electric universe type explanation for the tides, and his slides show that. The slides aren't in here, but I think they're on the video from last year. However, the electric attraction is a different matter altogether. Proponents of the electric universe point to the electrical connections between the moon and the earth in addition to the sun and the earth. The sun has a positive charge, the earth a negative charge. Since structured water also has a negative charge, and I think it was in 2013, there was a presentation, I forget his name, on structure, on there's a fourth state of water.
Dr. Pollack.
Yeah, and that was a very interesting discussion, and I think Scott was alluding to that. The sun has a positive charge, the earth a negative charge. Since structured water also has a negative charge, it is pushed away from the earth and drawn towards the positive charge of the sun. This is very much like a bowl of water being drawn towards the balloon. And I guess there's some experiments where if you suspend the balloon over a bowl of water, there's actually like a little bulge that shows up there.
Yeah, that charged balloon can actually bend the water.
Yeah, and I think he showed a picture of that in his slides. And I assume since he's admitting that the moon has an effect, that he also considers the moon to be positively charged like the sun, and the earth negatively charged. He didn't really put that in here, but an electrical force could also explain the antipodal tide, that is the high tide on the side of the earth furthest from the moon. Diagrams of the Earth's magnetosphere correspond to the crude schematics of the tidal forces. And he showed a picture where you have the Earth's magnetosphere stretched out on the far side due to the solar wind. And he's basically saying, electrically, you can see why there would be tides on this side and that side of the Earth. And so that was it. So we had a big debate. It was a debate, well, you're dismissing gravity altogether, and so there was a big debate going on. And I sat there and I said, yeah, this is really interesting. I never thought about that. Is there an electrical explanation for the tides? I don't know. I mean, what about gravity? So I decided to look up on Wikipedia and stuff, just what explains the tides. And apparently, since Galileo or even earlier, there's been a lot of explanations. None of them were that convincing. The one that seems to be the most accepted is going to be one from Newton. But the way you just think of it, why Earth experiences high tides or low tides simultaneously on opposite hemispheres is not intuitively obvious. If due to the moon's gravitational force, and a lesser extent to the sun's, one might expect a tidal bulge solely on the near hemisphere. You think about it, yeah, it's pulling more here than here. Why doesn't it come out looking like an egg or something? Since Isaac Newton, the accepted explanation is the differential gravitational force of the moon across the diameter of the Earth. The approximate tidal acceleration, which is axial, for the distances r considered, along the axis joining the centers of a larger mass and a smaller mass, its acceleration is approximately equal to plus or minus, which the opposite directions, 2g m of the larger mass, the radius of the larger mass, and the distance between the two masses cubed. So we see equal magnitude accelerations for the maximum tides, plus or minus the exact same value. This implies symmetry. And so so that explains it. The tides are explained, differential gravitational force of the moon. We have symmetry, problem solved. Additional websites cite the hemispherical opposites as symmetric based on polynomial expansions and neglecting terms beyond the second power. Oh, all right, so that whole talk last year was irrelevant, right? The tides are explained. Why are we even questioning this? The presumed symmetry, the figure, you'll find this a very common figure. This shows the tides, so it's pulling out equally on each side. The moon's over here somewhere, pulls down at the poles. The presumed symmetry is due to an approximation that holds when the radius of the affected body, in our case the Earth, is much less than the center-to-center distance from the affecting body, for example, the moon. And roughly, the radius of the Earth compared to the distance to the moon is about 2%. The exact solution indicates an asymmetry more pronounced as the assumption loses its applicability. So when I was looking at this, I said, well, why bother with the exact equation? Isn't hard to solve. Why are they playing games with this polynomial expansion? I was wondering, is this because they can't get equality of the tides without that? So originally I was trying to come up with alternate explanations for the tides. I thought I was wasting my time when I saw this explanation on there, but I still was bothered by the fact that there was an implied asymmetry if I did the exact solution. So I said, okay, I'm going to focus on examining the asymmetry. Notice that this is Newton's solution. It's a static case. You've got a static ball here. The moon is static. Rotational effects, orbital effects, there's no discussion of that. There may be, Laplace did a lot of work on this as well and has like 3 or 4 couple differential equations that give you pretty good predictions empirically. Whether or not they make physical sense, I don't know, but he certainly was able to get a much better approximation of the tidal behavior. Using the exact versus the asymptotic solution shows that an asymmetry between the tides will result for equal angles theta on the Earth's far and near hemispheres. This asymmetry occurs for both the magnitude of the differential force, delta G, and the angle of the differential force. For the near hemisphere, the moon's gravitational force at the surface of the Earth is almost always greater than that at the Earth's center, because the surface of the Earth, except near the poles, is closer than the center of the Earth. As you get near the poles, around 85 degrees, then it's equidistant. The opposite holds exclusively for the far hemisphere, where the moon's gravitational force at the Earth's center is always greater than at the surface, because on the far hemisphere, the middle of the Earth is always closer than the surface. The geometry here, we assume the moon is a distance d from the center of the Earth. Earth has a radius of r. I define 2 angles, theta f and theta n, which I set to be equal angles on the far side of the Earth and the near side of the Earth. So I'm basically looking at a symmetry here of 2 points, one on the near, one on the far side. The distances from the moon to these 2 points are d sub f for the far side, d sub n for the near side, and these create 2 triangles. One for the far side, phi sub f, one for the near side, phi sub n, which is a little larger than phi sub f. And so I'm going to use these to do my geometric examination with the exact solution. On the next slide, I guess it's losing its power here. I take the 2 triangles on the next slide and examine the forces. So on the near side, that's what my triangle looks like. This is what my force looks like. This is my delta G.
Okay, give that to me. I got a new battery. Just keep
Okay.
talking. I'll take it right back.
I have here is the delta G. So on the near side, on the part of the Earth facing the near side of the moon, this is the net differential force between the moon's pull at the surface and the moon's pull at the center. Basically, I mean, the differential theory says that because the poles are different at different locations, you end up with a differential force, and that's the cause of the tides. On the far side, this is your force triangle, and since the pull at the center is greater than the pull at the surface, you get a delta G in the opposite direction, and that leads to the bulge on the antipodal side. Again, going back to here. In my diagram, here the moon is here. In my diagram, I put the moon over here. But basically, you see the two slanting different directions. But what this shows here, the implication here is it's perfectly symmetric. You'll see in my pictures that without doing any approximations or anything, the delta G near, and these are drawn to scale, is going to be a little bit larger than the delta G on the far side. The angles, the beta angle here and the beta angle, pi minus beta angle here, are also different. So here's the math. And for convenience, I set G equal to 1 and M equal to 1, the moon and the gravitational constant. This is the calculation, law of cosines for delta G on the near, delta G on the far, beta on the near side, beta on the far side. To compare corresponding angles theta on the near and far hemispheres in terms of the differences between the differential forces in magnitude, the delta G, and direction, beta, calculate the following pair of differences as I go from theta equals to 0 to pi over 2 on each side. So I'm basically just sweeping up the far side, sweeping up the near side, looking at the symmetrically opposite points. And what I calculate then is the difference between the differentials, delta G near minus delta G far, and the difference between the angles beta near and beta far. And if we had pure symmetry, as is implied by the Newtonian explanation, these should always be 0 for all angles. For convenience, assume d, the Earth to Moon distance, is 1, and express the Earth radius as a fraction of that, which turns out to be 0.0166. And then I vary the ratio of the radius to the distance from 0.001, where the approximation should be very good, to 0.5, where the approximation should break down, because the approximation is based on r over d being much less than 1. Otherwise, you can't drop the second and third and fourth order terms out of the expansion. This is the results of the analysis for the difference between the differential forces on the near and far side. We'll start with this one here. This is the actual Earth-Moon ratio of the Earth radius to the Moon distance. This is in percent. And what this shows is when theta is 0, which would be at the equator, it's the maximum difference between the differential forces is about 10%. As you get closer to the poles, it eventually drops off very much. And you would expect that because as you get close to the poles, those two triangles that I showed earlier are almost exactly the same. I did the same calculation for a very small radius to distance ratio, which is in blue, and as expected, the difference is much smaller, it's less than 1%, and the difference increases up to almost 100% at the equator when I use 0.5. The key, though, is that the shapes of these are pretty much all the same. You get the maximum difference, as you would expect, the difference between the differential forces at the equator. The minimum would be at the poles. Similarly for the angles. Again, here's the Earth, the actual Earth-Moon radius. This is again in percent. Again, we see about a 10% maximum difference between the angles. The angles don't vary much at all when the R over D is very small. It starts getting significant as you get near 90 degrees because you get much sharper force angles near the poles. But generally, you see even here, you're still looking at about almost 100% difference in some of the angles. So what this tells me is that you do not have symmetry when you work with the exact solution. The symmetry is a result of the approximation, which drops out the second, third, and fourth order terms. And again, this is not a hard calculation to do. There's no need to do the Taylor expansion. I don't know why. I suspect that one reason they Taylor expanded is to come up with an excuse for symmetry. The expected trend that the moon's gravitational force on the near hemisphere, albeit decreasing from theta equals 0 to 90 degrees from equator to pole, versus the far hemisphere, again, equator to pole, always increasing, it's always greater for corresponding values of theta, is evidenced by the differences remaining positive. The difference is, obviously, the differential force on the near side is going to be greater than the differential force on the far side, because the far side is farther away from the moon, and you got a 1 over r squared dependence. It's not symmetric. And it decreases from theta equal to 0 to 90 degrees. Again, as we showed, those graphs, they tended this way. So as you got near the poles, the difference was minimal. But as r over d increases, as you move the moon or whatever your attracting object is closer to the affected object, this asymmetry becomes more pronounced. As a result, the differential force on the near hemisphere, although decreasing from 0 to 90 degrees, always exceeds the differential force on the far hemisphere, which also always decreases as you go closer to the poles. As an analogy, come up with the ring spring. I got an elastic ring with a spring across its diameter. It's fixed at one end, and then I pull it at the other. The ring expands in the direction of the force linearly, such that what was the center point of the spring is still the center point of the spring. It's still equidistant from both ends, and it's basically, it's still symmetric, except it looks like an ellipse. Continuing with this analogy, now I got a freestanding ring spring. Then I pull it equally on both sides. I get the same expansion, the same symmetry. It basically looks the same as the previous one. This one and this one look exactly alike. Note that the stretched ring spring appears the same as before. It's elliptically symmetric about its midpoint. The only difference is here I'm pulling from both sides. In the first one I fixed one side and I pulled from another side. This first case, this is essentially kind of what the differential force is sort of implying, except in reality, the Earth really isn't fixed here. The Earth gets pulled, the whole spring gets pulled a little bit by the moon. It's not fixed, but the implication here to get perfect symmetry is that the Earth would have to be locked in position when the moon pulled on it and affected the tides greater than it affects the solid part of the Earth. Slide 12, the first one, illustrates the assumed tidal effect for the asymptotic case where the radius over the distance is much less than 1, such as the tides are symmetric on both hemispheres. The force pulling at one end of the ring spring with the other end fixed, such as the moon, translates into a differential force as if pulling at both ends, which was the second slide. An observer in the middle, before any force is applied, sees both ends of the spring as equidistant and the ring as circular. After the force is applied, the observer still sees both ends equidistant, although farther away, but equally farther away, and the spring stretched to form a symmetrical ellipse. So that's basically the traditional explanation of the tides, is that they bulge out at the equator, or where the moon, in the moon's ecliptic plane, symmetrically on both sides, even though they're only being pulled on one side, because the pull on the surface is greater than the pull at the center on the near side, and the pull at the center is greater than the pull at the surface on the far side, so it kind of stretches out like that. Here's what I think really is going on. Let's go into space with my ring spring, where there's no gravity and thus no deformation. So I'm on my spaceship, it's hanging from the ceiling, there's no gravity, it's a nice circle. Then I decide to pull, only with the force, I'm pulling it downward now, force at the bottom, and again, this is not any different, except I turn the direction around from what I had when I pulled in this direction here. I got my nice symmetric ellipse, and I've got my nice symmetric ellipse again, except it's vertical. Now I let it go, I'm back here, and I decide to enter a gravitational field. Now the spring starts getting weight, and the top of the spring feels more weight than the bottom because there's more of the spring there. I'm not pulling or anything here, I'm just letting gravity and the weight, the now acquired weight of the spring, do everything. And actually what I would expect to get here is an asymmetric deformation that's sort of elliptical, but it's not really. It's a little slightly egg-shaped or something. This would be like as if the moon was pulling here, on the Earth. Now the deformation is not uniform, and an observer originally at the middle of the spring, here or here, now he's here, he's going to be closer to this end than that end. When he was at the middle of the spring, when the ends were equidistant, now we'll see the upper end farther away than the lower. The ring also deforms into more of an egg shape than a symmetric ellipse. This is the analogy for the case where the radius is not significantly smaller than the distance. This parallels the results from the analysis as shown in slides 9 and 10, which are my graphs. That is, there is an asymmetry between the two hemispheres, more pronounced as the radius gets closer to the distance. You get too close, you got Roche's limit, and everything pulls apart, so I'm not going to, that's a whole different presentation. Explaining the Earth's tides is not intuitively obvious, but appears to suggest an expectation of symmetry on the two hemispheres, that is, equally high tides and equally low tides, diametrically opposite. I mean, this is the traditional explanation that you get based on differential forces started from Newton. The analysis performed here suggests that this symmetry is the result of an approximation, usually quite good when the radius of the affected body is much less than the distance between its center and that of the affecting body, for example, Earth-Moon. However, exact solution of the differential tidal force equations demonstrates that there always is an asymmetry more pronounced as the affected body radius approaches the center-to-center distance from the affecting body. This peaks at approximately 10% in terms of the magnitude and direction for the exact Earth-Moon system, which would be at the equator. So I stopped the paper here and said, okay, I don't have symmetric tides. The explanation that I read with this approximation doesn't really satisfy me, but because the moon is so much farther away from the Earth than the Earth's radius, I guess it doesn't bother anybody. So I remember from last year's talk, Bob DeHilster brought up the barycenter motion. I said, well, let's see. Would that have any effect on this? Maybe this would help me getting something a little more symmetric? Can the Earth's monthly rotation about the Earth-Moon barycenter, which is about 3/4 of the radius towards the moon side, so it's still within the Earth, could this affect the tides? The sidereal period is 27.32 days. The tangential speed at the far side equator along the Earth-Moon axis is 29.4 meters per second. Compared to the daily rotational speed at the equator of the Earth, which is 463 meters per second, this is small, 6%, but it's not negligible. So I'm going to throw it out. I mean, it might have an effect. At the Earth-Moon axis on the far side, the barycentric centrifugal force on 1 kilogram of ocean is about 8 times 10 to the minus 5 newtons. That's significantly greater, about 70 times, than that differential gravitational force on that side. Even at the near side, where the Earth's barycentric rotation is slower, the barycentric centrifugal force, about 10 to the minus 5 newtons, is still about 10 times that from the differential gravitational force. So the centrifugal force from barycentric rotation is significantly higher than the differential force, yet the differential force is accepted as the total explanation of why we have symmetric tides. It appears that the dynamic effects from barycentric rotation should dominate over the static effect from the moon's differential gravitational force. So I looked at this and I said, okay, here's the difference between the green is the ratio of the barycentric radial to the differential radial forces on the far side of the Earth from the equator at 0 degrees out to 90 degrees. Clearly on the far side, the differential force, or the barycentric force, is 70, 80, even almost 90 times the differential force. On the near side, it starts out low, around only 10 times, goes up, and of course it meets at the poles where they're symmetric, again around 82 times. This is the actual barycentric force difference, and it's scaled to 10 to the minus 5 newtons. And if you remember from the calculation, on the side, the barycenter is 3/4 away from the center of the Earth. So on one side of the Earth is 7/4 away from the barycenter. The other side is 1/4. So on the side where it's 7/4 away and the Earth's surface rotation is maximum relative to the barycenter, The force was about 8 times 10 to the minus 5 newtons. There's the 8 here, this is scaled. And on the near side, it was around 1 times 10 to the minus 5, and that's the 1 there. So clearly, this isn't going to do it for me either, because I'm not getting any symmetry out of any of this. So neither the exact solution to the differential gravitational force approach, nor incorporating the effect of the Earth's barocentric centrifugal force established this alleged symmetry of the tides across the Earth's hemisphere. So once again, another dead end. So that was Appendix 1 to the paper. Said, well, let's try one more thing. An interesting anomaly that might bear further examination is revealed if one combines the barocentric effect with the moon's gravitational force directly, that is, ignoring the differential effect. I said, okay, what happened? I might as well try this. I'll get another couple pages on the paper. At the near end, there's the near side equator and the far side equator. The moon's direct, not differential gravitational forces on 1 kilogram of ocean water are fairly close. I mean, the only difference between the distance to the moon is the it's 12,800 kilometers of the Earth, and the moon is about 300,000 kilometers away. But it's a little different. On the near side, it's 3.43. On the far, 3.21, 10 to the minus 5 newtons. Now, if I combine these with the barocentric centrifugal forces that I already measured, yields net forces radially outward on both sides. And in one case, you add them together because the barocentric force and the moon's direct force are in the same direction. On the other side, they're in opposite directions. But when I add them together at the equators, I get almost the exact same forces, 4.63 and 4.61 times 10 to the minus 5 newtons. These are essentially equal, both radially outward, inferring symmetry of the tides at these highest points. Again, the equator, the ecliptic type thing. Is this just a coincidence, or might an explanation for tidal symmetry rely on this combination of forces, that is, including the moon's direct rather than its differential gravitational effect? These are the plots that I got from this analysis. Starting here, this is the difference between the combined barocentric centrifugal and gravitational direct forces. And you can see the difference here. I'm looking at 10 to the minus 7 newtons. So it's pretty small. Even with the difference of the angles of the combined forces, I'm looking at, 0.001 degree or 0.001 radian. The ratio of the different forces to the average force in terms of percents, here, the ratio, there's not much difference here. I'm close to 1% for my ratio, and it only, for the angles, it never drops too much. It drops a little bit for the forces, but only at the poles, where you magnify the directional effects. So these curves were kind of suggested that maybe if I combine the barocentric effect, which is a rotational effect, with the static effect of the moon's pull, could that be an explanation of the tides? If we consider the moon's direct gravitational effect, then what about the sun's, which is 180 times stronger? Can't throw the sun out here. The moon's direct gravitational force on the near versus far side differs by about 7% relative to its force at the Earth's center. For the sun, this difference is only about 0.02% relative to its force at the Earth's center. The sun's so much farther away, despite its much greater gravity, the difference in the sun's gravity across the Earth is only 0.02%. When considering the effect of the differential gravitational forces, the sun's is an important contributor. When we're doing a differential, if you read on the Wikipedia site, the sun's effect is, differentially, is about almost half that of the moon's, and that explains why you get neap tides and spring tides and all that type of stuff, supposedly. Nearly half the value of the moon's. However, when you deal with the direct gravitational force, the variation across the Earth due to the sun's gravity can be neglected. That is, it affects the Earth on essentially an equal basis everywhere, 0.006 newtons. Thereby won't introduce any asymmetry. So I can kind of drop the sun's effect from my analysis here. So in conclusion, just like the Earth's rotation is equal everywhere, I don't have to take into effect the Earth's effect. Is there an alternative explanation for the alleged symmetry of the tides other than accepting the approximation employed when deriving the differential gravitational effect? If the essentially uniform effects from the sun's and Earth's own direct gravitational forces, as well as that from the Earth's daily rotational centrifugal force, introduce no asymmetry, Might the combination of the barocentric, centrifugal, and Moon's direct gravitational forces explain what has so far been attributed to an approximation of the differential force derivation? And with all apologies to Scott Wall and the trouble that he started, and I haven't brought in any of the electric universe theories, not that I'm dismissing those, but this was a pure path down the gravitational world. Does this explain the symmetry of the tides? Thank you.
You know, I'm going to have to live with my dad for many years on this, because with the very same, he's sitting there, I told you so. So now I have to listen to that. See, I got it right. Dave. But it was quite a lively discussion last year.
Oh, yeah.
I mean, I don't know, we went on hours.
Mhm. Oh,
talking
yeah,
about
we
that.
were just.
My dad just got up and walked to the screen without
Well, he brought up the
permission.
barocentric effect, and then we had the electric discussion. This didn't come up because we didn't mention the differential last.
Didn't mention the
Wait.
differential last year.
Ray?
Yeah.
I wanted to thank you for doing the calculations for me. because
Oh, okay.
I didn't-
Wait, Ray, who suggested you do this? I asked you to do
I
it.
started doing this, I actually started doing this during Scott's talk last year. I started drawing the things, because I was just sitting there, because he was just talking about the direct gravitational effects. And clearly, the sun's effect dominates, the Earth's own gravity dominates anything, so there shouldn't be any tides, because the Earth's gravity is 1,000 times greater than everybody else's. So why do we have tides? He was saying it was electrical. You mentioned the barocentric effect, but it would be asymmetric. So I got home, I talked to a friend about this, and he looked it up, and he said, oh, Newton explained it to 400 years ago. So I looked it up and said, oh, differential gravitational force. So I read about it, and I looked and said, well, why? I said, okay, well, maybe that explains why there's bulges on both sides, but I don't see why they're symmetric because of the approximation.
Could I have a suggestion, please?
Sure.
As a comment. Okay. In my point of view, even the moon is not there. The Earth will have at least one tide every day. The reason is the sun effect.
The sun is going to have an effect. Correct.
Okay. The reason is not the effect from the sun directly. It is the traveling, the circular traveling of the Earth, and then it produces centrifugal force, swing the water away from the sun. So if you look at on the plane cutting across the Earth and cutting across of the sun, you will see the water body in a X shape, with thicker water on the far side, thinner water on the near side. So when the Earth spins, once every 24 hours, it must go to the sea, the far side. The far side have high water, so it's one tile there, and then because of the tilting of the axis, in the spring you see the higher water is in the north hemisphere. Half a year later, you will see the thicker water on the far side, on the south hemisphere.
But it still wouldn't be symmetric, would it?
Okay.
No, not symmetric, but time-wise, it is symmetric. Every 24 hours.
But it's right now the theory is that when we have a high tide here in Chesapeake Bay, over in the Sea of Japan, there's essentially equal high tide. They're symmetric, and the explanation is it's the approximation,
And then,
differential tidal forces.
and then even without the sun's existence, but the moon now, the moon also courses once every 24 hours approximately. And these two actions will cause some location see 2 times of tide, 2 times ebb every 24 hours. And I would, since you are interested in that subject, I will put up this suggestion and see if you can put it into consideration.
Well, since I did the first batch of calculations, I'll invite Bob to do that. He can just add on to my calcs.
That's only fair, I agree.
It's something that will be by considered it's true. So after the Newtonian gravitation and the electrical field universe explanation, something like that, I just thought maybe to add the thermodynamical aspect. So in my presentation, I indicated how the orbital movement of Earth around the Sun proceeds under influence of two counteracting two components, one over r squared and one over r to the third degree. One gravitational, the other anti-gravitational. Then when I showed those two slides to indicate the same forms of dependencies on the level of very elementary vortexes, like electrons, like protons, and so on, then getting in mind that electrons and protons are actually fluid vortexes with just the maximum density at areas that we maybe most easily perceive. Then you can think that also Sun is one giant vortex with the outskirts reaching to the Earth and to the Moon and to the other planets. And also Earth is one less giant like a vortex. So that actually in the movement of the Earth around the Sun and everything, we're actually having something as cogwheels, three-dimensional cogwheels. And then also that the water as a matter comes into it and somehow gets squeezed out and squeezed in. You know, it might be too far fetching, but you know, I mean, it might be really kind of different dynamical and maybe just really back to this. Down to the ground explanation.
I just wanted to.
I appreciate that, not even but kind of because of those whole problems, this and that.
I was just questioning the traditional explanation for the tides, because to me it does not produce symmetry, except when you make this approximation. And I don't see why. What I did was not a hard calculation. Why did they go to the approximation, other than by dropping out the higher order terms, you get symmetry? I think it's a fudge.
This paper doesn't belong in our group. It's totally mainstream. I mean, you could publish this in a mainstream journal.
I submitted this to Progress in Physics, and the response was, if I expanded the approximation out to all its terms, I would get the exact same answers I got from looking at the exact equation. I said, well, that's my whole point. My point is that by not expanding the approximation out to all the terms, a false sense of symmetry was created that wouldn't exist if you expanded it all the way out or just solved it directly. But since obviously it counters the main, you just don't understand the tides, you don't understand this, that's the typical response.
Wow. This is controversial.
Charles.
If gravity is due to vibrating neutral electric dipoles in all of matter, all of the atoms and everything, there may be some electrical variations that are occurring due to the interaction of the dipoles, and but I have never looked at that.
Scott, as I said, Scott's presentation last year presented an electric explanation, basically, and the Earth has a negative charge, the Moon has a positive charge, so it pulls the water towards the Moon on the near side. So then you get a redistribution of charge on the Earth's surface, and there's a repulsion on the far side, and that establishes the symmetry. That was basically his contention. And I liked that. I thought that was a really good explanation. And then I looked this up and I said, differential gravitational forces, darn it. And I looked at the equations, gee, it seems to make sense. But I said, why did they truncate the analysis? And that's what led me, so I focused on asymmetry for this.
Russo had a question.
Yeah, go ahead.
Yes?
Yeah.
Yes. If you have tide on one side of the earth, there's water rising. What happened to the other side, the opposite side, if it is not water?
Well, that was the whole, that's the,
No, it's not. Let me get it to display again.
yeah. I gotta go back to slideshow. this is, again, this is, I mean, this is what you think it should happen, right? It should pull the water towards the moon, and the water should come sloshing over here, so it look like an egg. I mean, that's what you intuitively think. But obviously, it doesn't happen that way. We do get opposite tides, whether they're symmetric or approximately symmetric, I don't know. But I mean, clearly, this isn't what's happening. So why? And so here's the traditional explanation. The moon is over here in this diagram. So the surface of the Earth, where the water is, gets pulled stronger than the center of the Earth. And actually, I'm looking down here. That's the polar axis. So it gets pulled stronger than it does at the center. So there's a differential gravitational force, and this is the whole explanation for when planets come within Roche's limit, or when, I forget, what was it, the Hale-Bopp comet came near Jupiter, got ripped apart. It's the tidal forces. The moon Io experiences these every day, and so the volcanoes are always erupting. So on the near side, the surface is getting pulled more than the center, so the net effect is a bulge in this direction towards the moon. On the far side, the center is getting pulled stronger than the moon's pull here. So again, since the center is pulling away faster than that, you end up with a net effect in that direction. That's the way they explain it. It has nothing to do with rotation or anything like that. And theoretically, if the moon came close to the Earth, it would turn into a sort of a pseudo-ellipse and then rip apart.
One of the things that I mentioned last time also is that we have continental tides, not just water tides. And so when you do gravitational measurements on solid land, it's moving up and down, and you have to have compensation for that. In addition, there is a tidal bulge on the moon, and there's no water. That's all continental tide on the moon, which ultimately causes the tidal lock and why the moon goes around. So it's not just water, it's continents.
Is it symmetric?
Is it symmetric on the moon? We probably don't know, because we don't have any probes on the far side to see what the bulge is with the near side.
I used to work for the Weather Service, and they predict the tide, the height of the tide, all around the world. So there's some place you probably could see that to find out if you think it's. But it may vary from one latitude to another.
Well, I mean, the depth and all the shape of the. I mean, it's almost impossible. But theoretically, with a perfect sphere surrounded by water, it should be symmetric, and that's their explanation. Is that it should be. We expect symmetry because of the approximation, and I say that using the approximation is cheating, and you should use the exact equation, and you shouldn't declare symmetry.
An eclipse, I was in California visiting before I moved out there. There was a solar eclipse that day, and I don't think you want to be in California when there's a solar, you have the moon and the sun and the earth in alignment, because San Andreas is right there.
Sorry, I don't think you answered my question.
Okay.
I said, what happens if the opposite side is not water?
It should be a less pronounced effect. Again, like Bob was explaining, on the moon you have no water. Still, you should still see a continental bulge. This part of the land should be pulled a little bit more strongly than the center, so the net force would be in this direction. So you would see a earth tide, which you probably do actually. I mean, it's dwarfs compared to the water, but this is not water dependent. It's just that.
Actually, the atmosphere itself.
It pulls.
Yeah. Okay. It should be the exact same thing, but to a lesser degree.
You mean we could have sandy tide, like in the Sahara Desert? That could be a sandy tide?
Same tide, yeah.
Maybe. I mean, I'm not. Again, I mean, the whole thing with this differential stuff. It bothers me with this differential stuff, because I mean, obviously, the moon is not pulling the Earth apart or anything like that, so
Responding to
Just bring
his continental type, why the moon keep facing the Earth. Theoretically, actually, these two bodies are actually still the same one, except that the moon, because of centrifugal force, and gradually pulling apart. But theoretically, in history, long time ago, they are the same body. That's why the Earth has the density, mass density, much higher than any other planet. But the moon has much lower mass density because the Earth grabbed the moon's gravitational, the mass center, still inside the Earth. That's why the angular momentum of the moon still maintain the historical momentum and keep facing the Earth.
it would be really interesting if Pluto had oceans, because there the barocentric effect would be much greater, because Charon, the dominant moon, is relative to the size of Pluto is fairly close. Maybe it's half or a third the size, and it's also, and they're not that far apart. I think the Pluto-Charon barycenter is actually between the two planets. If there was liquid water or some sort of liquid on Pluto, we could actually measure it. It would be interesting to see what tidal effects, because certainly you're going to dismiss the sun that far out.
One more suggestion to somehow transcend the masses and the gravity and so, and go farther away in the space. So it happened actually a month ago in Belgrade. There was presentation, set of presentation, so, and those people from Astronomical Observatory came up with some results on the distant stars, where they, by day, very, I don't know, them and some other people as well, by those spectrometry methods, very precise, very good, they were detecting kind of movements on distant stars, some movements, some bulges of matter going around, and people, mainstream physics did not support that. There was some reason why that should not be the case. You know, I would not see any difference between mechanism of such appearance of such waves or such tides there and tides here. We're looking at the ether and structure of ether, and then matter getting in and getting out and being moved around. It's like really kind of the vortex sense of the.
It's too bad Venus doesn't have a moon, because it's probably got a molten surface, and we could see maybe we could see some effects if it had a moon.
There's another aspect of the barycenter, because if you take a picture of the moon and the Earth orbiting the sun, they orbit like this. They don't. Okay, now the barycenter.
Like the binary stars.
The barycenter is going in the elliptical path, the two objects. So we're actually like binary planets. It's not really kind of an Earth and a moon. It's like two planets, and the Earth. If you then put a pin on a circle, make a circle piece of paper, put a pin where the barycenter would normally be when you had the moon, and you move that, the Earth is moving around that barycenter, and the moon is moving around that barycenter. They're both moving in a circle around the barycenter, and they're both going around the sun like that. It's a very, and that's another aspect of tidal waves, that motion.
So Ray, what in your judgment has this changed your? If you're drinking with your buddies at night and you're going to say what you really think, do you think this is a better model?
Than the pure differential? Yes, because it gives me symmetry, which the pure model cheated, in my opinion, because they truncated it. I mean, it may work for the Earth because R is much smaller than D, but what if R wasn't much smaller than D? Now again, this is coincident. I mean, my analysis here used the exact Earth moon. We have only one place in the universe where we can actually measure tides, and that's our planet. And they happen to appear to be symmetric. So I said this could be a pure coincidence, But I don't think the differential explanation is correct because, if R is closer to D, I'm going to get an asymmetry. So I don't. We may be unique. Maybe
Right.
there's nowhere else in the universe
Right.
where you have symmetric tides. It may just be because of the masses of the Earth and Moon and their distances that the barocentric effect tends to counter it. As the Moon moves farther out, maybe it will lose it.
Okay.
Maybe when the Moon was closer.
So
we
you're
would
saying the
lose it.
symmetry is just is what the accidental part
It
really
may
is?
very well be.
Okay.
So you know the tides aren't symmetric, right?
They're alleged to be symmetric on the opposite sides of the Earth.
If you look at a tidal
He's
chart-
only saying there's one on each side. That's
Well,
what he
if
means
you
by
look at a tidal
symmetry.
chart where they show the levels, you always see go high, and the next one's low, high, next one's low. You can see a line through them as they go across the month, but you alternate between the neap tide and the high tide. I mean,
Yeah, the moon.
so I guess what I assumed was that they were asymmetric. We were seeing the high one, and then when the next tide came, it was peaking, but it was always at a lower level. They alternated. I always thought there was an asymmetry. They alternated between there's high and there's then they one
Not
goes
all
up.
hot,
Not all the high tides are the same.
Right, but
But what I'm saying is that at any given moment, the two high tides and the two low tides
Yeah.
by this model are supposed to be equal. If we had if we had a pure sphere with water, and we didn't have any we didn't have any continents and stuff and ocean bottoms messing stuff up, this explanation says we should see pure symmetry. And the fact that pure symmetry is approximated is basically said, this is the reason. Yet, again, my approach was, it only is the reason if we ignore the higher order terms in the expansion. And why do you need the expansion? It's not hard to solve. I mean, you use Taylor's expansions when it's hard to solve the equation, the exact equation. You don't, if solving the exact equation is easy, why bother with approximation?
So you think they actually probably put those in because they could then explain symmetry, and we're just lazy scientists?
I have no idea. I mean, if this comes back from Newton's days, I mean,
Yeah.
Newton was smart enough to know this. I don't know if they knew if the tides were symmetric back in 1600s or not. I don't know if they even cared. But I mean, clearly the mainstream has grabbed onto this, and this is the aspect. The tides are explained. There's no more debate on just like there's no more debate on relativity. There's no more debate on black holes and gravity waves. The tides are settled. The moon's differential gravitational force causes it. Case closed. If I write a paper questioning this, I'm an idiot.
Okay, excuse me, one more point. When I was looking at this on the internet, I found a graphic that someone had done, and it was a graphic that showed motions of tides, but it also showed the continents. Now you want to see a mess. When they plotted, and I assume they did this somewhat logically from values of tides, high and low tides, you've got it almost looked like waves in oceans, kind of moving back and forth here and moving over here and moving over, and making this simple example look like it's so far off, it's ridiculous, because the Earth isn't. I'm not.
There's currents going on too. It's
not a perfect sphere with 10 kilometers of water all over the Earth, which is the way we try to describe it here. And there's nothing wrong with that. But the reality is, it's really kind of a very strange picture to watch. Now, whether the guy did it right or not, you kind of have to believe that it isn't that simple.
Those guys that I mentioned, they saw that from distant stars, right? Exactly like that.
Yeah.
The problem is that water is very sensitive to both forces. And one is a gravitational force, another one is a centrifugal force of the planet movement. And these forces are persistent there. So that the water has to respond, both forces.
So,
One other phenomenon that's related is hunters notice that when the tides would be, if you were in the ocean and you're on the land, that the animals are all more active. and they're feeding and doing stuff like that. And so they're able to sense whatever is causing the tides
Because of critical food.
Are they more active at the high tides or the low tides?
at the high tides.
The high tides.
Well, actually, they're if the moon's on the directly overhead or is on the other side of the earth, it both
Okay,
times.
the high tides.
Yeah.
Yes? Please, if your explanation is correct, there shouldn't be a bulge on this side. It should be in opposite side. It should be a trough.
Well, that's, if it's not, if, that's what got all this started last year. It should look like this. If the only effect on the tides is the direct gravitational effect, then it should look like this. It doesn't look like this. It looks like that. And the explanation that is mainstream or whatever is it's differential. My point is that I think without the Earth's barocentric effect, it would look like this. I think it's the fact that the barycenter is here, so the centrifugal force over here is greater than the centrifugal force here as the Earth spins, even though it only spins once every 27 days. Well, the Earth's, it's not the Earth spin, it's the barocentric, which goes about 1/27 days. Still, that's enough to bulge the water out here more than here, and it may be pure coincidence, but if I combine this picture, and if I were to draw a barocentric picture that would look like this, and I add my two eights together, it would be symmetric.
So you're just going to modify and say the tides are caused by the gravitation of the moon and the barycentric or part of the orbit.
As a purely gravitational explanation, that is one possibility. I'm not discounting the fact that maybe it has nothing to do with gravity at all. Maybe the Earth. I mean, if I do when I first did this, I did a strict gravity. I include the Earth's gravity, and I said we shouldn't have any tides at all. The Earth's gravity is so much greater than anything, sun, moon, whatever. I don't see why we have any tides at all. And so I said, but we do have tides, and they follow the moon. So I gotta get the moon in here somewhere. And my first thought was to make the moon. I made the moon positively charged. I said the moon's getting hit by a bunch of cosmic rays, a bunch of protons. It doesn't have a magnetic field to deflect it, so the moon's a big positive charge. Water is neutral, so the moon on this side pulls the water, the negative part of the water up here more, the positive part of the water down here. The Earth gets negative here, and the wind distance is negative here, and so the negative charges on this side of the Earth get pushed out more, the positive charges less. So I could see where a one-sided effect electromagnetically might yield asymmetric tides. And so I said, well, I like that answer. You know, I was with Scott at the time saying, I like electromagnetic explanation. Then I talked to a friend of mine, he was interested, and then he said, oh, look, check Wikipedia. The explanation is real simple. It's a differential gravitational force. I said, oh, darn it, I was hoping I had a whole new explanation. But then when I read that, I said, well, there still seems, I mean, yes, it makes sense mathematically, but it still seems to be short in that it doesn't give me the symmetry that's alleged.
I just want to make sure I understand. You're saying that there are two tides today, and that they're both equal.
Well, they're at any one point.
No, you're getting mixed up. What he's saying is at an instant. He's not talking about over time. He's talking about at one instant. So if they're both low equally on both sides of the Earth. If they're both high equally on sides. You're talking about over time.
I'm comparing this. Look along any diameter here.
Well,
Along any diameter, the tide on the opposite surfaces are theoretically exactly equal by the approximation of the differential gravitational force. But they are not by the solution of the exact equation.
okay, so I'm misunderstanding. Okay, so you have two tides. You're saying there's a bulge on each side.
Right.
Every 12 hours, the other bulge comes around.
The bulge just, yeah, the bulge just, as the Earth rotates, the Earth rotates under the bulge. The moon stays here, the Earth rotates, so Here you're in Sydney, Australia, an hour later you're in Brisbane.
This is what you're saying, and this is why.
This is the polar axis.
This is what's happening. Jeff, this is what you're talking about. He's saying that they're equal.
Okay, in this cross section, you look at.
But if I'm stationary on that bulge, and the one bulge comes around,
But the
and
idea
the next
is
one comes around, it's low.
Okay,
It's not over
every
time.
six, we're talking about the stars, right? It will be important to,
Well, that's
waving, right?
That's not true. I mean, this here, you can see there are 2 tides a day. If I stay at one
Yeah,
tide,
but
I don't
that's
have
not
one
what.
tide here.
But that's at one point.
The symmetry
We're staying at
and
the same
the
point.
unequal tide levels are being
But you're-
confused.
but if I'm-
The symmetry
Yeah.
he's
I
talking
mean,
about.
You're mixing the points, guys.
He is not mixing the point.
No, he is. No, what we're talking about. Look, I'll say it again. Here's the Earth. Watch. They're going like this. It doesn't matter if they're small.
What happened here?
It
What
doesn't
happened
matter
here
if
and
they-
here? What happened here?
We're not talking about.
This is Sydney,
But we have to
Australia.
talk about
Okay, if I'm, okay, am I in Sydney?
Here I am on the equator. Here I am in Cairo,
You're
or
adding
something like
You're
that.
adding overtime. He's not doing.
As I rotate here, I get a low tide. I rotate back here, I get a high tide.
Right, those 2 high tides are not equivalent.
Unless,
They are.
unless you're going to dispute
Oh,
the
okay,
tide
well, I
tides.
just wanna make sure
Yes,
that's-
they should. According to the differential formula, those 2 high tides should be exactly the same.
We observe them to be roughly the same.
Yeah, we
And they
do.
probably are.
Yeah.
And that's because the approximation is good when R over D is much less than 1.
Okay, so, like on this chart here, there's there's 2 tides in a day, one of them's higher than the other one. Where's the lower tide on that chart?
It's just smaller arrows.
No, that's low tide.
This is the low tides here.
Okay, there's a difference between low tide and 2 different peaks.
These are the low tides here.
There are 2 different valleys and there are 2 different peaks a day.
Yeah, but you're doing this DT. He's not talking over
I'm just talking
DT.
about what he's talking to. I'm saying that every day you have 2 high tides and 2 low tides.
Right, that's fine.
Okay.
They're just equal on both sides of the earth, is what people are saying.
All
charts.
the high tides are always high, that's all he's saying, and the
But the
low
high
tides
tides are not
low,
always the same
but-
height.
but-
Oh, no, that's okay.
Because
That's
the Earth,
understood.
the Earth isn't a pure sphere surrounded by water. There's
No.
continents, there's currents,
He's-
there's all sorts of things
He's not
that
talking about
mess
the
it up.
symmetry of change. What he's saying, he's been saying it all along, the Earth and all the stuff in the stars, all that will make differences. But in general, it should be, if it was only gravitational, egg-shaped. What happens is, yeah, there's differences, there's land, there's all kinds of things. But in general, tides are seen high and low, 4 times a day, 700 times a day on another planet, doesn't matter. They somehow are equal. And what he's saying, that's probably coincidence, just like when we see the eclipse. Why is the moon almost the exact same size? It's a
I
coincidence.
guess he's saying that there are 2 tides a day and both high tides are equal.
No, he says tides on both sides, no matter where they are in time. I don't care.
There's a high tide on each side of the earth.
Can you get that animation from somewhere to look?
Yeah. Well, this is why it went so long last year.
Everything would be clear in that case, you know?
I could be wrong, but somehow
You are right. You are right.
No, he's not, because you're over time. He's not talking about over time.
I'm talking about instantaneously. There is always 2 tides going on. There's 2 high tides. On
Sure.
And they should be equal if the Earth had no if the Earth was a smooth ball with a smooth delta water.
You know, my point would be,
But
they
you're a
would
physicist, so
they would
not-
go
right.
over continents if those continents would have been flat.
We're not talking over time. We're talking at an instant in time.
In an instant time. If I take
If you
a
want to
photograph
write a
of the
paper about overtime and all that sloshing around, you're welcome to. But this analysis is an instant in
Right, instant
time.
time. I'm taking a picture of the top of the Earth. He said at the axis, right? And I'm
Right.
looking at it, right?
Right.
There are 2 high spots and 2 low spots.
Thank you.
Okay. Right.
Okay.
But he's looking at the equator when they're equal.
That's fine.
That's all, because he's interested in the moon causes this.
Right.
Trying to simplify
I'm just
it.
trying to make sure that I understand because according to what I understand, those low spots are not equal. And the high spots are not equal.
Okay, but are you now talking out of the plane of the moon?
Yeah, I know. And you don't really have
I
it quite
don't.
all.
I'm just saying that what he
but-
showed.
But
up
you
there,
are.
There was the high.
What I'm sorry, look at his analysis. It's simple. It's just simple. Earth, moon causes tide. Okay, that's what moon causes tides equal on both sides. Doesn't make sense for people who look
When I
at
looked
gravity.
it up, I said,
But that's
Lots
what
of
we
people
observed.
have. Galileo took a shot at it, Newton took a shot, Laplace
Listen to what I say.
has
If
a
you take
bunch of equations that
a
actually
12-year-old
take
and
into
say
effect
gravity
constants,
pulls,
he has the best predictive
they're gonna say,
model of
oh,
what
the
actually
moon's
happens
over
on
here, it's
Earth.
gonna pull on
He's
this
taking
side,
into
this side is gonna
account
pull on.
the shapes,
That's what
the
that's
currents, but
intuition
it's a very
says.
complicated set of
Okay, the
coupled
distinction
differential
between what I'm
equations.
saying and what you're saying is, I'm not arguing that
Taylor's
it's
advantage
crazy
of
that there are
his
two
theory
high
now.
tides.
Well, he looked empirical.
That- I'm just
Yeah,
saying-
he just said, here's the tides,
I'm
and
just
here's the
saying
way to
that
get it.
I don't
And he-
think
yeah,
that they are
he
observed to
came
be
up with a
equal.
set of equations that would.
There is, they
reduce
are
the
asymmetric.
tides
Look,
at
there's gonna be a little
certain
difference, but in
location
general,
wherever he did it.
they're equal according to the
I mean, obviously, every
measurements.
place on Earth that has single.
I'm talking
they know
about,
what
and I'm
the
not
daily
talking, what I'm
tides.
talking
They
about is,
measure the
well,
tides, and they
unless,
can
unless
predict them
everything they're
beautifully,
telling
but
us
it
is
doesn't
wrong.
give you the physical
Well, I'm
explanation for
But
it.
you know,
This
like
is-
there's
there's
a
a-
baby.
This is one side.
It makes sense.
Well,
But at
again,
every
I mean, the
point,
differential
makes
is
it
One
every-
side, you're talking about one
Yeah,
side.
one
we're
point,
talking
I'm
about-
talking about 1 point over time.
In
What you're
Japan
much
and,
less than one, so that-
New
You're
York.
saying, okay, I can measure a high tide on one side, and on the other side I can measure a high tide.
Right, and
Just
they're
because
they're
it
pretty much,
works
they're
doesn't
close.
But he's saying that, like
It should
here
work
at
the exact
Alexandria,
solution
they have a high tide twice a day.
Well, yeah, I know,